Sorry, I mute myself. Could you guys hear me?
Yep.
Okay,
Yep.
thank you. Appreciate. Sorry, I just mute myself. So, yeah. Any question about homework number 1? Okay, if not, that will do on Thursday, before 12:30. And then, so if you are not familiar with the Sakai, or you never done it before, like saying it's submit your homework through Sakai, upload the files, sort of things, you need to let me know. The 12:30 is a hard deadline, so you might want to try to upload a file before that, so it would be easier to make sure that the file is uploaded correctly. Okay, and then so far I haven't heard anyone tell me that it's those 2 midterms on Fridays doesn't work for them. So I will give you a week to explore or look through your calendar. So if I still haven't heard anything on Thursday, then I would make an announcement saying that 2 midterms are going to be on Friday afternoon for 3 hours. Okay, so keep in mind, if you do having any complete, possibly not going to do on Friday afternoon for 3 hours, you let me know. Okay, we could see, I will see how things go. By any means, if like too many people tell me Friday afternoon doesn't work, then I'll move to just in class on Thursday in the same week. Okay, good. So let's finish our.
I have a question.
Yes, please go ahead.
I accidentally submitted unfinished homework. I have one part of a question I forgot to do. So can I just send like the complete one directly to the grader?
So is that Sakai prevent you to submit another version?
Yeah, I think I cannot resubmit the assignment.
I think, yeah, because I unchecked the resubmission button. I thought that's for after the submissions you could resubmit or not. Yeah, so send it to me. That's easier. So I would know you are in time. So then I will forward it to the grader, and then I will make sure that I get a file. And then okay. So yeah, so next time I will just check that resubmission. So for you could whenever you don't like it before the deadline, you could submit another version of your homework.
Okay, thank you.
Yeah. Anything else? If not, okay, let's go on to the trying to finish the transformation. So last time we end up talking about it. Okay. Whenever you univariate, you could use in CDF or Jacobian. Now we move on to so-called multivariate. Then but we begin from a bivariate. In that case, to the discrete random variable bivariate, it will still. So let me see. Yeah, hopefully it's not too thick. So then bivariate right here, we're still like counting. Hold on. So bivariate right here, if there are 2 discrete random variables, it will still like counting. Okay, last time we talk about whenever you are Poisson distribution, x1 and y1, both are Poisson. Then if I want to do new random variable, which is x plus y, let me go there. Then how we are going to do about deriving the new random variables. Let's see, okay, yeah. Then how I'm going to talking about doing new random variables PDF then. If it's like a discrete random variable, nothing but counting, like this guy right here. If you're trying to derive in the PDF, say u is x plus y, and then if u equals 3, then how do I derive a probability of the distribution of u? Nothing really, but what? Counting, just making up every possible cases for u equals to 3. In this case, I can basically is 0, 3, 1, 2, 2, 1, and 3, 3 and 0. And for each one, you can calculate the probability because x, y are independent, so nothing but times 2 probabilities. That should be trivial. Okay, so then in the general case right here, I can really think what? I can really fix x and then look at how y changes and then fix x at x, then y of course equals to 3 minus x. And then this guy right here, nothing but having these two probability times together because of independence. Then for each one, you're just using Poisson's PDF for x, Poisson's PDF for y, with different lambda 1 and lambda 2. That's it. So I think that's easy. And then what if you do have continuous variable, which is much more important in our class actually. We don't do too much about transformation on discriminant variable, but we do a lot on transformation of continuous random variable. Okay, let's get started from the bivariates. And then you will find out that Jacobian method is going to be the first one you are going to use whenever you have a chance to deriving the joint PDF of bivariate distribution. Okay, so say x and y original random variable, and right now if you have the transformation, usually what we deal with is two random variable, have the transformation to creating two new random variable as well. So right here is I want to transform x, y into u, v, and through that two functions, g1 and g2. Okay, then in order to using Jacobian, there are some conditions. So either in statistics, or in mathematics, whenever you feel like you're looking at some theory, some derivation that they told you, this is my regularity conditions, or this is my conditions, keep in mind, you ask yourself, where does that condition apply to? Does the condition making sense? Okay, you trying to figure that out. So whenever you want to do new theories, you know how to write down that necessary conditions. It's actually okay for you to have as many conditions as possible, but just like as long as you apply more conditions, your math is more limited. Okay, so you're thinking it's the ultimate method would be is what? Really flexible, not much of limitation, not much conditions apply in general cases. Okay, that's how we have a stronger results or weaker results, or stronger theory or weaker theory. Okay, but you shouldn't mind you having that conditions written down line by line. Okay, it's better clear than vague. That's it. So then ask yourself, hey, why I don't need G is 1-to-1 on S? S would be the sample space of X and Y. Why do I need that? All right, I actually write it here. So the reason I need that is I want that inverse function will define it. That means if I can have G1 and G2 are all 1-to-1 function, so when I find inverse function, I don't have to talk about it to mapping to which domain. Okay, much more easy. But this one, could this one be relaxed? Yes, you could. And then like we talk about partition methods, it's really nothing but partition into some 1-to-1 functions. Okay, and then the second condition would be, hey, G has to be continuous, and then partial derivative on S. Why do I need that condition? Not hard to imagine. Remember Jacobian? Okay, yeah. So how in asking about when you ask about 1-to-1 onto, yeah, I'm saying about 1-to-1 onto. Okay, but 1-to-1 is much easier for people to imagine. Okay, so remember Jacobian is dealing with the first derivative. So if you do have that continuous function. You're doing partial derivative. It's much more straightforward. You don't have to worry about which domain is actually continuous, which domain is not. Okay? So all I write here, it's much easier case for you. In my class, not necessarily so difficult in terms of like spatial cases things. So, well, it's a master, right? So it's not necessary to be that general in every case. Okay, but we learn from basic first, then trying to think about extension. Okay, that's my philosophy about approaching a theoretical class. So sometimes you would think, well, it's too naive. Well, maybe, I don't know. So, but let's see. Okay, so then Jacobian is non-zero right here on S. And then you think about why do I need Jacobian is not zero, right? Now to imagine, isn't it? If your Jacobian is zero, what happens? Your PDF is zero. Okay, good. So PDF is zero basically is what? Basically useless PDF. Okay, but we do have a good name for that, so-called degenerated PDF. Okay, but again, it's yeah. If you want to be solid, you're talking about, hey, I can have my PDF is zero. Why not? Right? I have degenerated. Yeah, you could. Okay, but in this case, we want it more regular. So that means I'm assuming whenever you have a transformation, your Jacobian is not going to be zero. Okay, good. Yep. Then, as you can see right here, if I do have those three conditions satisfied, if I can derive everything as smooth as it can be, I don't have to worry too much about where the domain is. Then the new joint PDF of U and B. Okay, so right, 2 to 2 transformation, right? I have original joint PDF XY, and not deriving the new PDF, joint PDF of U and B. Right here, still same way as univariate case. Okay, you do find inverse function for U and V. Okay, and then plug in to the OPDF X and Y, and then just finding that Jacobian. Okay, the same philosophy. Okay, but the point right here is right now Jacobian become 2 by 2 matrix. In the univariate case, doing the first derivative and then differentiation, then you get that a single number of scalars you can plug in. Right now, it's a 2 by 2 transformation. You did do get your Jacobian matrix. It's a 2 by 2 matrix. Then you'll find out that there are different ways to write their partial derivative. Either people will say partial x, partial u, and then partial x, partial v. Okay, or you might say, well, when I learn my calculus, I write partial x right here, partial x right here, partial v, and then partial y, partial y, partial u, then partial y, partial v. Could I do that? Yes. Okay. So I think in that week 763 class, I said Jacobian matrix is symmetric. I'm totally wrong. Okay. They are not going to be symmetric matrix. I'm thinking about Haitian matrix metric. Right now, they are not symmetric matrix, that's for sure. But the determinant, after you deriving partial differentiation, eventually you deriving the determinant of the matrix. Then, no matter what way you write it, the determinant will be the same. That's all I meant. All I meant to say, it's not symmetric matrix, but determinant is the same. Okay? So remember how to do the determinant of the 2 by 2 matrix? Okay, remember times chi, right? You times your diagonal, then minus your off diagonal. Easy calculation. Okay, good. And then imagine what would happen if this 3 by 3 matrix. We'll talk about that later on. Good. So then I think the approach is kind of easy to remember. Really, I have my transformation written down, find the inverse function, then plug the inverse function to the OPDF, then derive Jacobian. That's kind of typical steps we'll have. Okay, let's take example right here. Okay, right now I do have x is gamma, then alpha 1 and 1. Okay, another PDF y is gamma, alpha 2 1. Okay, then this is my OPDF, and then xy are independent. Okay, much easier to handle. And then I do have the transformation u is x plus y, and then v is x divided by x plus y. Okay, so my goal is trying to deriving u and v's joint PDF, right? So then derive transformation, nothing but what? Finding transformation function, deriving Jacobian. That's it. And then the first step, deriving inverse function. Okay. Then, like I said, it's, if you can't imagine what inverse function means, just keep in mind it's working your best to put x and y in the left hand side as a function of u and v in the right hand side. Okay. By doing that, what would that be then? So this guy, you can imagine x is from here. X would be v times x plus y, right? And then good life is what? Good life is x and y equals to u. So I can just write v and u right here. Okay. And then since I have x is v and u, then y nothing but u minus x, right? From here. Y nothing but u minus x. Then x is v and u. Okay. So maybe easier to just put e and so u and then 1 minus v is. Okay. Possibly. I'm saying possibly. That's the way it is. Okay. Good. So then new PDF, again, OPDF equals to new PDF, x and y right here. And then plug in inverse function from where x is, from where y is. Okay, nothing but plugging, then working on the Jacobian. Okay, so Jacobian right here, right? You could say, well, I'm gonna partial x first, partial u. It's easier for me to say this. That's easier for me to remember. Okay, again, you can remember different ways or different directions, going to row or going to color. It's up to you. But at the end of the day, it's you should have an identical determinant. Okay, partial x, partial u is v, right? Then partial x, partial v is u. Okay, then partial y, partial u is 1 minus v. Then partial u, partial y, partial v is what? Partial u minus uv should be minus u, right? Okay, slow down to make sure that I did not make any mistake. My u and v look awfully similar. So let's do that. So then I think so. Yep. And then the Jacobian nothing but this guy minus vu, then minus u times 1 minus v. And it equals to what? Minus vu plus vu cancel out, become minus u. But then you put down absolute value to make sure that it's positive. That's a u is. Okay, I like it. Clean Jacobian, much easier for you to derive in a joint PDF right here. Right? Okay, so that means I get your u in Jacobian, then you could write down formally then, hey, this is new joint PDF I'm trying to derive. And then what is a joint PDF of an x and y then, right? You want to figure out. And then in this case, x and y follow gamma alpha 1 1, and then gamma alpha 2 1, and then x, y are independent. So the joint PDF, because independence, nothing but times marginal PDF together, and then you memorize, or you actually pull out the distribution table to write down this is alpha, and then beta right here is 1, I think. 1, right? Yep. And alpha 1 is 1. Then x, alpha 1 minus 1, e minus x divided by beta. Beta is 1. Okay, so you do the same thing. So I can really just simplify it, because 1 whose power anything is 1. So I could just write y, not x. Y right here, alpha 2 minus 1, then exponential minus yx. Okay, good. So far, so good. Then you could actually write a much more simplified form. You could possibly write it as alpha x, alpha 1 minus 1, exponential minus x, alpha 2, then y, alpha 2 minus 1, exponential minus yx. Okay, that's your joint PDF of S and Y. So that means you can actually plug in, say, maybe I can write it alpha 1 and alpha 2 together because it's constant. So I plug in right here, right? VU. I plug in where the X is right here. So that means this guy is VU alpha 1 minus 1. Then exponential minus VU. Okay? And then I plug in U 1 minus V is where the Y is right here. That means U 1 minus V with alpha 2 minus 1. Then times exponential minus U 1 minus V is. Okay? Of course, don't forget about your Jacobian U right here. Otherwise, eventually you'll screw up everything. Okay, otherwise, eventually you won't see what I'm eventually prove U and V is independent. Okay, then after that, right here, you wanna what? You wanna simplify. Okay, to simplify, you want to put your V together, do your best, and then put your U together, do your best. Okay, so I will do that. So 1 alpha 1, they are constant. If you don't write it, it's actually fine, but I write it every time. And then look at my V. I have alpha 1 minus 1, right? And then this guy right here also is having V. So that means since I have V alpha 1 minus 1, 1 minus V alpha 2 minus 1. Okay? Then, of course, I do have this guy V as well. I do have this guy V as well. But it turns out to be exponential minus UV minus U, then plus UV. UV cancel out. You guys see that? Okay, hopefully you see that. These two guys cancel out right here by U and U times V. So that means V is all you have right now. How about U? U will be U alpha minus 1, okay? And then also U alpha 2 minus 1, okay? Then don't forget about Jacobian right here, also have U as well. Then U right here is about Jacobian. Then, of course, you have exponential right here, right? Like I said, it's exponential combined together, minus UV cancel out, then eventually minus UX. Okay, good. So that means if you want to even simplify, I can write something down like this. V alpha 1 minus 1, what is V alpha 2 minus 1? Then I have U is what? Alpha 1 plus alpha 2 minus 1. Then exponential minus U right here. Okay? Of course, I will put comma right here. Is actually identify what? V and U's domain, right? You write join PDF, you find it, it's finished, yes, but it's better to have you to have something. Could you still hear me?
Yeah,
I think so. Okay, yeah, thank you. Appreciate it, because I don't see my talking point on the monitor, so I thought you guys lost me. Okay. Okay, sorry, apologize. This is what the online teaching would be. So you never know your internet connection is good or not. Okay, good. And in this case, I mean, I will give you something to deal with. It's much more complicated. You need to find out what eventually able to do transformation. Your domain of new random variable, not necessarily straightforward. But right here, lucky us, they are straightforward, right? Look at U is what basically it's X plus Y, X positive, Y positive. So then X plus Y, U should be also positive as well. So easy, right? From 0 to infinity, easy. And then how about V then, right? V is really what? A ratio to that sum of two positive numbers right here. What's the domain, right? It's a ratio to the sum. So domain, not surprising, should be from 0, bigger than 0, smaller than 1x. Okay, but again, I'll give you something which is typical questions my students have to deal with it. Finding a domain of easy transformation, still linear transformation, but the domain just not straightforward to find. I'll give you that. They'll teach you in that case how you having an easier way to find a domain. Good. Okay, right here we finish with deriving a joint PDF of a U and V. But going further, a lot of interesting things we wonder if that holds. For example, I do deriving joint PDF of U and V right here, right? This is my joint PDF of U and V. And people ask, does U and V are independent? Okay, that's number one. Number two is, okay, say if you're proving U and V are independent, could you actually tell me what does the marginal PDF of U and V is? Okay, good. So number one, does U and V independent? Easy to prove. Why is it easy to prove? Right here, of course, if I want to show that, I'm going to show is what? UV as joint PDF. If I want to show that independent, only thing to do is what? I show it as a product of marginal PDF, right? You finish proof. Okay? Yes, it's correct. But right here, you don't actually need to show that. If you want to show independence, you don't actually have to show that it's a product of the U and V as a marginal PDF. Actually, only thing you need to show it could be written down as two different functions or two separate functions for G1 and G2. G1 and G2 not necessarily PDF. As long as they are separable, you could basically claim that it's U and V are independent. Okay, in this case, it's true because this part is what? Function of V. This part is function of U, right? This part G1, this part is G2. I can separate them into two single functions. So I can show that it's U and V are independent. The reason for that is actually easy. As long as you can find G1 and G2 function, they are separate. If you want to make a PDF, then the only thing you need to do is standardizes. Standardizes it's just transform your G1 function to become some PDF. It's always not that hard to find it. Okay, so the reason why I don't have to show that G1 is PDF or G2 is PDF. I can always try to standardize the G1 and G2 to become PDF. Good. And then, of course, if you do find G1 and G2 are PDF, then you finish. Okay, then you find FU and then FV right here. Then making G1 as FU, making G2 as FV, you finish. But as always, like this question right here, G1 and G2 not necessarily PDF. Okay, so again, like I said, okay, if G1 and G2 not PDF, let's make it PDF then. For example, right here, look at G2 right here. Say for U function right here, okay, U function right here. The U function right here, I start from U alpha 1 plus alpha 2 minus 1, then exponential minus U. You look at this right now, okay? If you don't know what a PDF this one should be, I'll encourage you get used to it, okay? Which means when you look at U or X right here, exponential minus U right here, what kind of PDF immediately popping out your mind? This guy should be follow what? Nothing but gamma. Gamma PDFs always having that U exponential minus U same structure. Okay, then you pull out your distribution table, trying to match in, hey, this is gonna look like gamma. Could I match it to find my alpha and beta parameter? The answer is yes, right? This guy is what? Alpha right here, right? So that means I can put alpha as alpha 1 plus alpha 2. Because the gamma's PDF in terms of U as a power always like alpha minus 1. And then this guy's beta right here, right? This guy's beta in original PDF as a gamma. So that means because this guy right here divided by 1, so that means I can safely write down right here it's gamma alpha plus alpha 2 then 1. But you do have that constant right here to make it standardized as a gamma alpha 1 plus alpha 2 and 1x. It's nothing but gamma. This is what you need to standardize it. Right? Good. Then that make it whole thing as a gamma alpha 1 plus alpha 2. Good. And then you borrow something as a constant right here. Then you need to give it back. For example, if I have a V function right here, alpha 1 minus 1, 1 minus V, then alpha 2 minus 1 right here, right? This is a function right here. Okay? I do borrow gamma alpha 1 plus alpha 2. Then I need to give it back. Gamma alpha 1 plus alpha 2, right? To make it balance. Then the rest of constant is gamma alpha 1, then gamma alpha 2 from here. You guys with me? Okay, so that means these two guys come together, then become original joint PDF of U and V. And then again, you look at this. You imagine what this PDF is going to be. Okay, then let me teach you one thing. It's really easy. Whenever you look at something domains from 0 to 1, how many choices of standard PDF you have? How many distribution their domains from 0 to 1? So far, only 2 distributions, the domains from 0 to 1. What's that? One is uniform, right? Does this PDF look like uniform to you? Definitely not, right? And then another one, the domains from 0 to 1 is what? Beta distribution. Okay, good. And then you pull out the distribution table to look at this. You'll find it's, yeah, exactly. This is a structure of beta, having that V, then 1 minus V. Okay, and then you will find this guy. I think if I memorize correctly, maybe I can looking at my solution right here. Yeah, I think so. Okay, it's alpha 1, alpha 2 as the beta's parameters. Good. Okay, so that means we finished answering whether or not U and V independent, whether or not what's the marginal PDF of U and V is. Okay, good. And keep in mind whenever you finish your derivation, if you want to make yourself feel good, you should ask yourself, does my result making sense? I've told you the result making total sense. Why is that? Because I do know x is gamma, y is gamma as well. I have u as x plus y. Remember I told you gamma plus gamma will still be gamma. And then this guy, it's alpha 1 mean, then plus alpha 2 mean. 1x. Okay? After this class, you could actually write it down. I've guaranteed that you got to follow gamma alpha 1 plus alpha 2 because u is gamma plus gamma. That will be still gamma. Okay? But of course, the beta got to be fixed. That's a little thing you need to pay attention to. Okay? And then my v is what? X is x plus y. It's a ratio, it's a proportion of the v function. Then we know v is from 0 to 1. This guy follow beta. Nothing. This guy follow beta. Totally makes sense to me. Because beta is the domain with 0 to 1. Okay, good. That's a transformation, easy example to handle that 2x2 transformation. These 2 slides actually tell you the story. Okay, and then now how to imagine on Thursday when I give you homework number 2, you are going to deal with a bunch of 2x2 transformations. Great. Okay, so let's Jacobian. In any case, I can also using CDF. The answer is yes, but not that regular happens. This one is very easy example for me to teach you. In some case, CDF methods having much straightforward approach to answer. Okay, x and y right here, I do have a density of weird one is 1 over pi. And then the domain of x and y right here, it's not like x and y independent, it's more like x and y are not independent. The domain is in this kind of circle right here. That means if you do have the original system x and y right here, right, x and y, okay, everything right here is in the domain of from 1, from -1, from +1 in the circle, right? This domain of the x and y. I apologize for this ugly circle. It's really hard for me to draw a circle already, and then letting alone I'm just circle on the iPad. So then, but you know what it means, right? The domain is right here within the circle. Radius will be 1. Okay, good. And let's say if I do want to derive a new random variable, it's nothing but a distance from any point to origin, which means that, let me see if I can go on. So this is x and y. So if I do have any points right here, the distance to origin right here is nothing but u, random variable, right? Then x squared plus y squared and square root is nothing but distance from any point to origin, 0 and 0. Then if I want to know what the distribution of u is, then CDF method is really easy for you to handle. For example, okay, I can write down CDF u is by definition u smaller than little u. And I plug in my transformation, right? Easy. And then you deriving this guy right here, right? By taking out square root. So that means this guy becomes u squared. Okay? Then this guy right here, how do I calculate probability of x squared plus y squared smaller than this guy? U squared. Nothing but what? Nothing but calculate area of the inside circle. Right? Okay? Then, or saying it's actually inside circle proportional to outside circle would be. It's exactly how likely your sample is going to fall into that small pie right here as a probability. Then how do I calculate this u squared then? like I said it, right? So really is really proportion of inside pi, which is radius u square, I think. Oh, then u, yeah, u square. Wait, u, not u square, it's u. Right, u. So that means, okay, radius u. So what is the formula for the area of the circle then? Is that u squared times pi, right? Good. And then outside big pi, radius actually 1 because I have 1 right here. So that means it's 1 times pi. Pi cancel out and become u squared. That's exactly where this guy come from. Okay, good. So that means I have my CDF of u equals to u squared. Then PDF nothing but taking derivative become 2u, straightforward. Okay, so see, using CDF in this particular example, so easy to handle. How about Jacobian then? How about Jacobian? Okay, I'm not going to go to Jacobian right here. It could be your homework. I still wanna finding some good things for you to work on. But one thing you wanna imagine is this, right? So if I'm asking you, hey, only about x squared plus y squared, I have only one single variable as a transformation. But this example right here, you teach me is always about 2 by 2 transformation. If I only have one single transformation, it doesn't fit what you teach me. What should I do? What should you do? Then one common approach would be you creating another random variable called v, maybe equals to some easy quantity, either x or x squared. I think x possibly the one I would choose. Okay. Then you pretending this new random variable and then working on the x squared, then y squared, or x and y. It's a trick right there for you to do in terms of choosing x squared or y squared as a random variable. Then having that doing transformation function. Okay. So this guy right here is not necessarily easy doing Jacobian. It's possibly workable. If you see that in homework, don't be surprised. But one thing you want to keep in mind is, if I'm asking about transformation, it's 2 to 1 transformation, which means it's I have x squared or xy, then transform to u. Then if I'm asking you doing Jacobian, then you need to find another random variable v in some form of x or y, then using that to working on finding the joint PDF of u and v, using inverse function, using Jacobian, then eventually what? If I'm lucky, I do find u and v a joint PDF. How do I get the marginal PDF of u? Nothing but taking out v in your joint PDF, the way you did it in 660, to get the marginal PDF of u. Sounds good? And then it would be not hard to imagine if your voice pretty, right? Hopefully, cross your fingers, you'll find is what? You'll find it's your u and v are independent, like a case I show right here. U and v are independent. Then integrating out v is nothing but u alone. Okay? Good? So that means if they're independent, so this kind of process right here, you could actually just find out those individual v or individual v. Then if my day even prettier, those PDF is some standard form or some PDF of standard distribution X. Then so you don't have to working on so complicated integration to get a marginal PDF of u or v. Okay, but you know, life is always difficult, right? So you might not get an easy case when you're deriving the marginal PDF. But this guy right here is exactly what I'm talking about. Okay, so in engineer school, they're using so-called convolution formula a lot. Okay, it's always interesting to talking to engineering people because they are using different language from us, but they are using the same method. For example, when I say, well, this is random variable, they will say, oh, this is parameter, right? But parameter to us is what? Fixed values of theta. And then they call it constant. So really, this kind of language, different words, different disciplines. You need to get used to it. You need to, when you communicate with certain people in certain areas, you just need to pay attention to what they are talking about, because what they are talking about may be exactly the same as what you're talking about, but they are using different terminology. Okay, good. So convolutional formula right here is you do have x and y independent, good news. Okay, and a continuous random variable. And then a lot of times they are interested in deriving really the sum of the two random variables, which means I only interested in the density or distribution of z itself, the sum. Okay, but right now it's like I said in the previous one, is this is 2-to-1 transformation, which means I have two random variable only interested to one right here. Okay, then but the Jacobian method is all about 2-to-2 transformation, M-to-N transformation, M by N transformation, right? So then that means even though I really interested in X, I'm only interested in Z as X plus Y. And then how do I do eventual deriving the Z's PDF then? Using transformation method would be just assigning new random variable W. Okay, that would be much easier. Of course, you could still use CDF methods. That's another topic. Okay, but I'm not necessarily dealing with the complicated question right here. So let me give you a sentence. In this case, assigning a new random variable will give you much easier life because it's always easier to working on the inverse function and a Jacobian. Right here, inverse function, number one step, finding x and y in the left hand side. Right, in this case, very easy. W, y would be what? Z minus x. Z minus x would be so xw, y is z minus x would be w, then would be z minus w is this is the inverse function. How about Jacobian, right? Jacobian should be easy. Partial x, partial z, 0, partial x, partial w is 1, partial y, partial z is 1, partial y, partial w is minus 1. Okay, easy calculation Jacobian. This guy 0, this guy minus 1, so that means it's minus 1. I'm going to just write 1 right here. Jacobian is 1, so easy to handle. For example, right here, z and w, my all random variable, the same principle, trying to bring up x and y's join. X, yeah, z and w, all new random variable, x and y, all random variable, right? And then I plug in x as w, then z minus w. The same thing as I teach. Plug in inverse function. They having Jacobian is 1 right here. So this guy's 1. So everything you don't have to worry about. Okay. Of course, right here it's I don't x and y are independent. Good news. So that means I can write x w y then z minus w then because x and y are independent. Okay. So then so-called convolutional formula is really nothing but when I'm deriving the marginal of z, nothing but integrating out the joint PDF of x and y by what? By w. Right here. Okay? This one is our convolutional formula. Okay? But then I think convolutional formula is easy to derive, straightforward to use, but one thing always much difficult to determine is be careful about the range of w. When you integrating w, not necessary from minus infinity to infinity. Okay? W is x, so domain of w should follow domain of x. But sometimes the domain of x not necessary as minus infinity to infinity. You need to pay attention to the domain of w. So after you do integration, you'll find the right answer. Otherwise, you'll screw things up. Okay, good. So 123, hanging there, goes finish. The last page right here, also important, is so-called location scale family. I don't know if you learned that from 660. If you don't, it's okay. But location scale family is very important family. So number one thing is, why do we call family? Family means there are collection of PDFs we call family. And then location scale. What does that mean by location scale family? So there's a location family, there's scale family, combined together become location scale family. Then typical example would be normal mu sigma square. Okay, then mu is location parameter. Sorry, sigma square is scale parameter. So normal mu sigma square belongs to location and the scale family. Whenever you have a location scale family, it really easy to deriving a transformation whenever the new random variable x is a transformation of the standard normal, which is normal 0, 1 right here. Okay, so in the future, it's really, I would have to say that it should be straightforward for you to see right here is what you should. I don't want to keep emphasize it because I think this is something you need to know for sure. It's if you look at z, if normal 0, 1 right here. Okay, whenever something times sigma right here, the whole thing become what? Normal 0 sigma square. This is something I'm not going to keep saying because I think after this class, it got to be in your brain already. Okay, and then because whenever I talk about this, I'm going to jump. I just directly showing so. Okay, and then you plus mu, basically adding up on the location parameter. So everything at the end of the day is so straightforward to you. Is x is going to follow normal mu sigma square. Okay, but that's the results. Apologize for that. That's something I just become so natural to you in the future. But right here, I'm talking about, hey, how do I really show that x is normal mu sigma square by transformation method, right? So again, it's like I said, because I do know z, for example, is normal 0, 1, right? Then if I do have the x as mu plus sigma square z, sigma z, not sigma square z, sigma z. How do I how do I really like using more statistical approach or mathematical approach to show x is actually following normal sigma square? This guy nothing but transformation, right? X equals to mu plus sigma square. Then just like doing what we usually do is what? Finding inverse function, deriving Jacobian. That's it. So that means number one, okay, find inverse function, easy, right? So put your best to put z in the left-hand side, and then x minus mu divided sigma. That's inverse function. And then number two, Jacobian, right? dz dx, right, equals to what? 1 over sigma, right? dz dx. So that means this is the transform PDF I want to have. Then this is original PDF as z, normal 01. Then I plug in the invoice function. Everything is exactly the same like I teach you. Plug invoice function. Then don't forget about Jacobian. Okay? And then of course, if you do remember what is normal 01 is, right? 1 over 2 pi exponential minus then z then 2, right? 2 sigma squared is a 2 right there. And then what? And then by there you keep going. Hey, everything is what Dr. Lin talked about. You plug in, right? You plug in where the z is, x minus mu divided by sigma. Then there's a 2 right here. Of course, this square, right? I forget the square right here. Okay? Then you have that 1 over sigma as a Jacobian. Then you sort of summarize it. You will immediately to see that whatever transformation, that one got to be normal mu sigma squared. Right? This got nothing but taking your 1 over sigma into square root of 2 pi x become 2 pi sigma squared. And then this guy right here, nothing coming from right sigma squared, then go to the denominator, become 2 sigma squared x. Then x minus mu and squared in the numerators. Okay, then yeah, this is new PDF as x. Then you immediately know this is nothing but form of mu sigma squared x. Okay, so that means in the future, when you look at the Lorentz scale family, this is something you want to pay attention to. This guy is nothing but right now, right here. It's nothing but form of the transformations. Okay, good. So I finished transformation. Good timing for me to stop right here. There's 15 minutes to go. I can talk about the next unit. So before that, does any questions you guys have? If not, then I'm going to go to a random sample. I just put the slides in a Sakai this morning, so a little bit late. I apologize for that, but only 15 minutes. I'm not talking about pretty deep stuff, so you should be fine with that if you don't have that slides with you. But you guys are next to computer right now. It should be easy for you to get that slides from computer from Sakai site. Okay, so in the next unit, we are talking about random samples. This unit coming from Kassenberger 5.1 to 5.3. Okay, so in a transformation, it's more like a preparation for you to understand this. Then from chapter number 5 is going to be going to our more serious stuff. What we are going to learn this semester about statistical part of the inference. Okay, so number 1 is learn what does a random sample means. Again, random sample is I talk about it. What's the difference between data scientist and the statistician? Really, random sample is the difference. To me, maybe you have different interpretation about two roles. Good. So in this section, we are going to learn about it. Hey, statistical inference, okay, it really concerned about two entities. One is population, one is sample. Statistics is nothing but just collecting random sample to do inference on population. Single word, finish. Okay, that's what statistics all about. But sample has a different definition. Population having different definitions as well. So it's really going deeper. There are a bunch of things you need to take care of. Not just a single term, but in terms of conceptual wise, statistics, nothing but taking sample to inference on population. Okay, so then that's exactly what I said is the samples join from population and use that to make inferences what the population look like, For example, I'm drawing sample, I calculate sample mean, trying to estimate what the population mean is. Really so-called doing inference. Okay, in this section, we are going to working on the properties of the random sample weights. Okay, so for introduction, I think it should be easy for you guys, I think. So for example, it's you're doing like a drug research, right? You have new treatments for hypertension. Then you are going to sample of 50 hypertensive patients from UNC hospital, okay? And then you select it, you treat it, and then you are trying to look at what the outcome is. Visually, we call primary outcome or primary endpoint in biostatistics. So if you're looking at the primary outcome is reduction, whether or not my drugs actually lower the DBP. And then after treatment, then because you have 50 hypertensive patients, after taking a drug, you measure their DBP to see if it's lower. Then you have in that 15 numbers coming out, X1 to X50. Right here again, as like I said again, keep saying it, capital letter to us is a random variable. Little case to us is sample or observation or realization. Okay, but your X1 to X50 could be different type. For example, lower the DBP or not is 0, 0 or 1, right? If lower is 1, if not is 0. So X1 to X50 could be binary, or it could be just difference between before and after as the DBP reduce as continuous. Binary means you just need to recognize the distribution of the random variable itself. Then because sample size right here, right, of 50 is n sample size, you will know that. So like I said, it's X observed value or realized value, okay, of a random variable Xi, right? This become like professional talking. It's, hey, what does you mean by realization? What do you mean by realized values? Okay, when I talk about realized values, when I talk about observations, I'm talking about little case of X1 to X50. Okay, and then capital one will be random variable. So, which means that it's almost, I think almost, if like professional talking, you won't say X1, X2, then Xn are mutually independent. Nobody will say so, because when you write little case, that's fixed value to X. They are not random variable anymore. If you want to talk about so-called mutually independent, you put capital case, X1 to Xn. Okay, so in my in-person class, I was joking one thing is, you need to put 3 ... right? When you write statistical methods paper, when you write ... it's always ... only 3 points. Don't write dot or ... okay? It's always ... 3 points when you're trying to describing from X1 to Xn. So again, be professional. So always write ... when you're writing in your master paper or writing your dissertation. Well, your advisor told you that story as well. Okay, good. So then X1 to Xn is called random sample from population PDF. So right here, like I said, you are saying I said population using PDF, right? So read like saying it's PDF do have different names, population, model, in different area, people call PDF by different names right here. But by any means that PDF. By any means, if you know PDF, you know population. That's it. Okay. So of course, we do have a class for like a survey methodology. I don't know who teaches it this semester, but it's always good thing to learn about different aspects of the statistics. We don't have the abundance of class for you to choose, but some of them is you want to take a required and some are elected. Then you might not necessarily know what survey sampling would be, but I mean it's fine. But right here it's something like the same thing right here. Say if you're sampling from finite population, which means your total population size is known number. It's not infinity, it's fixed size. Usually using capital N right there to describing finite population. Then when you do your random sample, you need to pay attention to whether or not there's a replacement allowed, which means it's really like if you learn about your statistics 301, I think you have that like earn things, right? In the earn, there are 3 blacks, 4 rebels. If your one is black, did you put back? Then having different probabilities of the color of the next join, right? So that means the same thing as well. Although the earn problem is that's just introduction, but it's actually happened in the real world. Is do you want to make a phone survey to the same guy again? Okay, so if allow to talk to the same person again in the future, then that basically is who's replacement. If you're not going to talk about the same guy again in the future, that's without replacement. But either way, either with replacement or without replacement, it's okay to us. Only difference would be how do you adjust your estimation to reflect the true population. That's it. That's a key point. That's a big statistical issue for us to deal with. Okay, good. So then you also drawing one subject out of the population, you don't put it back. Then so-called without replacement. Again, this guy's example, right? 25 balls in the urn. Then you do have 3 blacks and 22 reds. And then that's a total 5. This is population right here. This capital N right here. Okay. Then of course, if you just like pull out your urn, then look at every balls, then you don't have random sampling. You don't have statistics, or you don't have statistics with random sampling. More like a random sample would be I do know inside urn 25 balls, I only draw 5. That's your random sample. Okay, and then but that X1, X5, you need to pay attention to does that with replacement or without replacement. Okay, then right here is a critical point I need to mention. And in my class as well, I think conventionally apply to every class of your statistic class about, when we say random sample right here, I want to emphasize it. When I say random sample, I actually means the IID. You know what ID is, right? Identical, independently distributed. So that means even though you imagine random sample could be you sample one thing out, then without replacement, don't put it back. But in that case, in my class, for example, it doesn't belong to random sample. That's the reason why, because it violates ID assumption. But does that mean it's not statistics? No, it's just statistics, just not terminology-wise. It's not random sample I meant. Okay? Then you will find out it's ID actually give your life easier. So the reason why I said it, if I told you random sample, things would become much easier. Okay? In this case, why I said this guy is not random sample then. Okay? Imagine this. So if you actually choosing the first guy right here is black, the probability of the next one is black easy, right? You guys having that degree of college, so you should know that what I mean, right? So the first one choosing black, that means the urn only having 2 blacks left, right? And then your urn only have 24 balls left. Among them is 2 blacks. So the probability, of course, is 2 over 24. But then if you recalculate only marginal probability, that means X2, I just sample that directly from the urns without first step. Then the probability is actually 3 black balls over 25 balls. Okay, so then what I said, they are not independent. Look at this, right? I'm taking out right here. right? So this guy definitely not equal. Then what does this guy not equals to this guy told you? That basically told me that it's x1 and x2 are not independent. Because if x1, x2 is independent, then this guy should hold, right? But it doesn't hold. Why? Because I can write this, right? x2 equals to b equals to b. Then given that x1 equals to b, then probability of x1 equals to b, right? I can write left-hand side of joint probability become conditional probability times marginal. That should be standard training of 660. And you'll find out it's this guy right here is nothing equals to this probability, like argument right here, right? So it means your joint probability is not product of the marginal probability. That means x1, x2 is not equal. Okay, so let me take everything out because I want to say one thing. It's what happened is n is very large. Right here, n is finite, 25. What if my n equals to 1,000? Much, much larger, right? Becomes what? If this guy right here, I have only 3 balls, this guy becomes 997 red balls. And then what happened? What happened is this guy still 2 balls, this guy become 996, right? Oh no, 999. And this guy become 1,000. What happens? What happens is how much different this guy and then this guy is. They are awfully close. You don't even tell maybe how many decimals they are different. What does this guy told you? This guy told you it's even when my n is finite, my 2 events, okay, my events may not independent. But when your n is population size really large, these 2 guys right here will be awfully close. I can basically treat them as independent. Even the procedure I did, creating so-called non-independent case. Okay, so here comes the final point I want to say. If I say this, I'm going to dismiss class. In my class, you do need to pay attention to your inference is on finite n or n goes to infinity. Okay, because when n goes to infinity, like this guy right here, then good thing is going to happen because you basically could taking out a lot of things. For example, non-independence, for you to not easy to do statistical inference. Or saying that is more precisely, it's when n goes to infinity, good thing would happen. A lot of things will cancel out. So your inference on sample size infinity would give you much better life, much easier inference for you to deal with. Okay, good. I all 1 minute over. So any questions? I would say the same thing on Tuesday. Again, I will keep telling you for you to inference under finite n or under n is infinity. So anything else? Any question? So if not, I'm going to say goodbye and have a good one. If you are 673 students, you guys are working with me for another hour from 2. Okay, so